relativistic because they move according to the Newton's equations, combined to the Maxwell's equations that are the equation of electromagnetics. So our system of equations is a bit long and sort of complicated, but it's written here. So there are two equations, ordinary differential equations for each particle, one for the momentum, one for the position, sorry, Q of the particle, J. It goes from 1 to capital N. So we have in principle N different charges, each one with its own mass, mj. Can you see my pointer? Excuse me. So if
yes.
I point, okay.
Yes, I can see.
So each particle has mass mj and momentum pj. Okay, so of course the first equation is a bit of trivial. So the derivative of the position is the velocity of the particle. Then we have the derivative of the momentum that gives us the coupling to the electromagnetic field. So rho j, this will be the same for also for quantum and for all the talk, and it will play an important role, is the charge distribution. So how the charge is of this particle is distributed in space. We can even consider particles that have zero total charge. If the charge is the total charge is zero and the distribution of the charge is homogeneous, of course, we don't have any interaction with the electromagnetic field. But we can think of charge with net total charge zero, but a non-trivial charge distribution. So some positive charge in one region and negative charge in another region, in a way that the total charge is zero, but still with a non-trivial coupling to the electromagnetic field through dipole or quadrupole or multipole coupling with the field. Okay, the setting is very general. Also, neutral, globally neutral charges are allowed. So there is the coupling of each particle with the electric field, the coupling with the magnetic field through the Lorentz force, and then there is the electrostatic interaction. This gradient J of V of Q is the electrostatic interaction between particles. If we have several particles, and since they are non-relativistic, the net effect in the non-relativistic limit, starting from the relativistic one, where all the interaction is mediated by the electromagnetic field, is the fact that we have the typical Coulomb, if they were point particle, electrostatic potential. Okay, then the next two equations are the equations for the true dynamical equations for the electromagnetic field. So the two of the Maxwell's equations, as you probably very well know. And the last two equations, that are the other two equations in the Maxwell equations, are acting as a constraint at this level. So if they are satisfied at the initial time, and they shall be satisfied at the initial time, they are satisfied for every other time. So the dynamics of this Newton-Maxwell coupling preserves this constraint, so these equations that should not be satisfied at any time, but it's sufficient that they are at the initial time.
Excuse me.
Yes.
May I interrupt you and have some questions, which is very elementary?
Sure.
Thank you. You are writing that it is equations for the particles. So I guess mj is a mass of particle, pj is a momentum of the particle. So maybe there are some finite number of particles.
Yes, capital N. Capital N is.
Okay, so as I guess, rho j is a kind of the charge density. So you are writing particles, but actually particle means kind of the crowd. I mean, each particle.
Yes. This is okay. This is a
it's a kind of a density. So kind of the crowd, and the density is given by rho j.
Yes,
Do I understand right? So that qj is a kind of the
center of mass, if you want.
Center of mass.
So the idea, this is an approximation that, okay, it's also sort of, well, it's not unavoidable, but to make the equations treatable mathematically, it's very natural. So yes, you are perfectly right. So the charge is distributed in an extended way, but there is an approximation for which this charge distribution is attached rigidly to the particle, to the center of mass of the particle. So we don't consider the motion or the possible deformation of the charge distribution in the motion, but we consider this charge distribution as a cloud, if you want, of charge that moves rigidly together with the particle.
Okay, so the electromagnetic field produced by the charge is the rho J.
Yes,
is E. Convolution between rho J and E evaluated at the center of mass, QJ.
Yes, yes. So yes, the charge distribution is evaluated in every point in space, but is moving rigidly. Since it's evaluated here, it means that we are shifting this charge distribution rigidly together with the center of mass.
Okay, so the rho J is actually the function of the time.
No, it's
No.
The function of time is this QJ. So the fact that here is a convolution, so where we evaluate the charge distribution depends on time through QJ.
Okay. So, but particle should move. But
the particle moves. QJ is a function of time. MPJ. So the center of mass of the particle moves, and it drags along the charge. Okay.
Yeah. Okay.
So in the convolution is rho J evaluated at x minus QJ, and QJ is a function of time.
I see.
So instead of being centered in zero, it's centered in QJ.
I see. Okay, so QJ is a function of time, so it means that rho J is a kind of a shifting in the function of time. Yes. Okay, I see. I understand. Thank you. Thank you.
Okay, you're welcome. Okay, so yes, indeed, this was actually a very good comment. Thanks, because yeah, it may be unclear. So yes, indeed, the charge is thought as a rigid object where the charge distribution moves without being deformed together with the particle, moving together with the center of mass of the particle. Okay, so these are the equations, and we have some problems with these equations. Namely, we have problems both when the distribution of the charge is concentrated in the center of mass. So we are talking about point particles, but also if the charge distribution is concentrated in a very small radius around the center of mass. So the first result that is very well known is that if we take charges, so the charge distribution to be a delta distribution, so concentrated in a single point, we have a problem. The electrostatic energy, so the term coming, the energy coming from this electrostatic force here, is unbounded from below, for example. This is not the only problem, but the most well-known and important one. So we have an energy, the total energy of the system is unbounded from below, and we would have that an atom, well, an electron that is a charged point particle in principle. If we don't take care of quantum mechanics or don't care about quantum mechanics, a classical electron will be accelerated in rotating around the nucleus, so it will emit radiation and decelerate because of that. And since the energy is unbounded from below, it will continue to decelerate continuously and will collapse on the nucleus in a finite time. So this is one of the contradictions that come from combining classical electrodynamics with charges distributed in a single point. There are also others, but maybe a result that is slightly less known is that even if we consider charges with a small radius, we still have some unphysical behavior of our system. And this is a result due to this to physicists Moniz and Sharp in 77 in Physical Review B. So the idea is that if we take a charge that is concentrated in a very small radius, you see there is this Bohr's radius that is here, 2EJ squared 3mj. So I'm taking C equal to 1 and the H bar equal to 1 if you want here. So this is the anyways, there is this quantity that depends only on your ratio mass charge ratio in each particle. And if you take the charge to be distributed all inside this small ball, the electrostatic energy is then bounded from below, but still we have some unphysical behavior. In particular, we have the existence of the so-called runaway solutions, so solutions that accelerate forever. So even if the particle is very much far away, isolated from where the original electromagnetic field was, still we have a continuous acceleration on the particle that runs away indefinitely. And also another non-physical behavior is that we have solutions that are called non-causal. So solutions where even if we turn on the electromagnetic field only at a certain moment in time, and you have one particle, the particle starts to accelerate before the electromagnetic field is turned on. So by feeling the electromagnetic field, but in a non-causal way. And this is due to the fact that one can write effective equations for the particles that involve the third derivative of the position of the particle. And if we have this charge that is concentrated in this small radius, we have that the so-called electromagnetic mass of the system that is becomes negative, and so we have some or zero. And in case it's zero, we have runaway solutions. In case it's negative, we have non-causal solutions. Okay, so I don't want to go into very much details on this because it's not really the focus of my talk, but just to say that classical electrodynamics poses problems for physicists and also for mathematicians, because even for mathematicians to make this case well-defined is sort of tough. This case can be made mathematically well-defined, but to prove that mathematically that there are these runaway and non-causal solution is not known. At least in my knowledge, there is no proof, rigorous proof of this effect, but there are some physical motivations that make this, let's say, reasonable, but I don't know of any actual proof of this. Okay. Anyways, even if there are these problems, especially in the physical interpretation, we can state a result of well-posedness for these Newton-Maxwell equations that I showed you. So we are taking the potential V, the potential that was the electrostatic potential, so this potential V here, to be nice enough. So we take it 2 times differentiable with continuous derivatives, continuous and bounded. This is just because of the mathematics. Well, one could maybe relax a little bit this assumption, but it's not really necessary. For example, with the charge distribution that we have to take, the true electrostatic force between particles will be of this type. So this is actually a physically reasonable assumption, combined with the assumption on the charge distribution that we have. If we consider this potential to be exactly the Coulomb potential between particles with the given charge distribution. Okay, so the idea is that if the charge distributions are all regular enough, and this regularity is written below, we have global well-posedness for the Newton-Maxwell system, where E and B are in some suitable Sobolev space. And the precise result is that if each charge distribution is an H1 function, so a Sobolev function in H1. We have that the system is globally well posed if we take both E and B, so the electric and magnetic fields, to be in H1 half. So each component, they are vector fields. So each component in the vector field should be in the space, Sobolev space H1 half. And so this means that if we take, we have those charge distribution, if we take initial data in for E and B in H1 half and any position for a momenta for the particles, we have at any time a solution, a unique solution of the Newton-Maxwell equations with continuity with respect to the initial data as well. Okay, so this is the well-posedness result that, let's say, was in the literature up to our work. And I will come back on this soon, but for the moment, let me stop with the classical, this classical electrodynamics and describe a little bit the quantum counterpart of this system. So quantum electrodynamics of non-relativistic charges. Okay, in this case, everything is quantized. So the particles are quantized and the electromagnetic field is quantized. And so we have an interaction between the quantum charges and the quantum field. And in this quantum, at this quantum level, we write this so-called polyfield Hamiltonian, that is the formal or actually rigorous quantization of the system, the classical system that I wrote before. We will see why it's actually the rigorous quantization later in the talk. And so we have this Hamiltonian H, capital H, that depends now, and I stress this dependence because we will study the limit H bar to 0. So we put this parameter H bar that is for us a semi-classical parameter that is, let's say, proportional to the Planck's constant. So we have this parameter. And the Hamiltonian reads like this. So there is the minimal coupling between the quantum momentum operator of each particle and the electromagnetic potential, vector potential, AJ. So this is the quantized electromagnetic potential. The explicit form is written below. It depends on the position operator J, and it depends on these A and A star that are the creation and annihilation operators that I will tell you about quickly very soon. Then everything is squared, and we divide by 2 times the mass, as it should be. Then there is the electrostatic potential acting on the particles. So this Q without any index is all the set of variables, so Q1 up to Q capital N. Okay, and then we have a free Hamiltonian for the field, this H field that is written here below. Okay, so let me comment a little bit on this, starting from this vector potential AJ. So as you probably again very well know, there is a gauge freedom in electromagnetism, also at the quantum level. But at the quantum level, to get rid of unphysical degrees of freedom, we should fix the gauge. So it's meaningful to fix the gauge to set up the problem in the correct Hilbert space. And we choose the Coulomb gauge because in this type of Hamiltonian is the most convenient gauge by far. It's not the only choice. We could have different choices, but this is the most convenient. The Coulomb gauge means that the gradient of AJ as an operator should be 0. So should be the 0 operator. And to impose this Coulomb gauge, we introduce this epsilon lambda of K. These are called polarization vectors. So there are 2 polarizations for the electromagnetic field in the gauge, in the Coulomb gauge, and they go in directions that are orthogonal among each other and orthogonal to the direction of K. K is the Fourier variable associated to position, And so we have a three-dimensional orthonormal basis if we take the versor associated to K, E1 and E2. Okay, so this changes for any K, of course. So it's a function of K, but of modulus 1 is a very nice function. Then for each polarization, we have one annihilation operator A1 or A2, so A lambda here, and the creation operator A star lambda in the Fock space, because the quantum electromagnetic field is a quantum field and lives on a Fock space. That is a space where we have one Hilbert space for each number of excitations of the field, because the field excitations can be created and destroyed. And so we have one subspace with 0 excitations of the field, one with 1 excitation, 2, 3, and so on. And we take the direct sum of all these excited Hilbert spaces, and this builds up the Fock space. If someone is not familiar with that, if everyone is familiar with the Fock space, you know all the properties that this space has. And this is a bosonic field, so we have a symmetry. So if we exchange two excitations of the field, we get the same result. The wave function shall be symmetric with respect to exchange of variables. And these operators A star and A make you jump between, so A star creates 1 excitation more, makes you jump from 2 to 3 excitations, for example, and A makes you jump down, so annihilates 1 excitation and it makes you go from 3 to 2, for example. Okay, so we have these two operators that their linear combination build up this electromagnetic vector potential. It's a vector potential because these epsilon are vectors, okay? So these are vectors here. So this is a vector potential. And of course, the electric field can be obtained by this vector potential by taking the time derivative, and the magnetic field can be obtained by taking the curl of this potential. Again, but this should be something you are all familiar with. The free Hamiltonian for the field is this combination of A star A with a dispersion relation that is a relativistic dispersion relation of a massless field that is this modulus of K that appears here. In addition, we have a dependency of all these operators on this semi-classical parameter H bar. So this is a quantum world. We have H bar everywhere. In particular, the commutator between the position and momentum of each particle is proportional to H bar with the proportionality I, and is non-zero only if we take the commutation of the position and momentum of the same particle. And the commutator between the creation and annihilation operators again scales like H bar. It's proportional to H bar, but now with the proportionality constant of proportionality 1. So this is written here. And you get to this one only if you take the same polarization. And then you have this delta. So this is actually a distribution. It's seen as a distribution. So you should smear with test functions properly. So there is a delta, not exactly a 1 here. I will not go into the very gory details of the Fock space estimates, so you don't have to worry too much about the creation and annihilation operator if you are not too much familiar with them. Okay, then the quantum dynamics, it's given by, so given a quantum state that is this gamma H bar, that is a density matrix, a trace class positive operator on the total space of Hilbert space of the system, that is consists of an L2 part for the particles and the Fock space for the field in tensor product. And then you put the unitary group associated to this H on the left and on the right, of course, as usual, to obtain the dynamics. Okay, so We have a Well-Posedness result also for the Pauli First Hamiltonian. This was the first result for arbitrary charges was given by Fumio Hiroshima in 2000, if I recall correctly. But there are then several other results on the self-adjointness of this operator or related operators with some increased difficulty. So we have global Well-Posedness. Again, we assume that this potential V is 2 times continuous and bounded. But we make a slightly different assumption on the charge distributions. So before we said we assumed that the charge distributions were H1. Here we take H dot minus half, minus 1. So H dot is the homogeneous Sobolev space. And we take index, negative index minus 1. So this means that if we take the Fourier transform of rho, we divide it by mod k. This is square integrable. Okay. And then we make the intersection with the homogeneous space of index 1 half, positive index 1 half. So we take the Fourier transform of rho, we multiply by square root of mod k, and this is a square integrable function. Okay, if we assume that the charge distribution is in this space, okay, that is slightly different from the one at the classical level. But if we assume this at the classical level, we are not able to prove Well-Posedness. This will come later. So let me preview that we assume only this regularity, and we try to use the standard techniques for like fixed point arguments and then energy conservation and so on to prove Well-Posedness at the classical level. We are not able with charge distributions that are in this with this regularity. But here at the quantum level, with these charge distributions, we are able to prove that the operator, the Hamiltonian, is self-adjoint on the intersection of the domain of the momentum operator for each particle squared and the domain of the free field operator. Okay.
Just a quick question. So the
Yes.
on the assumption on the charge density, is the first assumption essentially assuming infrared cutoff? I mean, not clearly, it's not a cutoff, but something like a
yes, some infrared
cutoff
regularity, exactly. We need some infrared regularity. Especially
perfect.
because, in fact, we could get rid of this, actually. Probably even of the, I mean, we could take rho in L2 and still have essential self-adjointness, but not on this domain. And especially, we may lose boundedness from below.
Okay, yes.
So
yes,
this
yes.
infrared regularity is ensures us that we have boundedness from below. Of the Hamiltonian.
In the second one is the ultraviolet cutoff. Yes, exactly.
Yes, exactly. There's the ultraviolet regularity.
Okay, perfect.
Okay, so comments actually in part related to this comment by Max is that okay, we have still some problems in the sense that it's a folklore that point charges should be admissible, so we could take rhos to be deltas, and of course they will not satisfy this regularity condition if they are delta distributions, but they should be admissible, but mathematically it's still an open problem to prove that this Hamiltonian with point charge distributions is self-adjoint. For sure, there should involve a renormalization procedure when one should renormalize the energy, so take subtract an infinite energy between quotation marks in some sense from the Hamiltonian, and one should also probably do what is called a wave function renormalization, so to change the Hilbert space in some sense. But it's again an open problem that is. So we don't know yet mathematically that this is indeed feasible, but physically it's let's say assume that it should be so that it should be possible through a renormalization procedure to define the electrodynamics for these charges, even if the distribution is concentrated in a single point. On the other hand, if we forget about the fact that we are not able to do point charges, so we still assume that the charge distribution is a bit extended, and this makes, as Max said, a ultraviolet cutoff actually on the system. So if the charge is extended, we have that very high momenta are cut off from the coupling. We can still allow for more singular potential electrostatic potential V's than in the classical level. In particular, we could take the Coulomb potential for V. At the classical level, again, let me stress that if we take the Coulomb potential between the particles, even forgetting that the distribution is extended, we are not able to prove well-posedness of the dynamics. So the electrostatic problem is cured by taking the quantum mechanics. As we know, the quantum atoms are stable, and they involve there is only considered typically the electrostatic force between the nucleus and the charges, the electrons that are around the nucleus. So atoms are stable, as I said, in quantum mechanics. And also, even if we take small radius, there are no problems. So we can take small radius, but a very smooth charge distribution that satisfies this regularity assumption. And there are no runaway or non-causal solutions at the quantum level. So those physical contradictions that emerged at the classical level seem to be cured at the quantum level. So yeah, quantum electrodynamics is a more fundamental and a more proper way of describing at least very small charges moving and interacting with the electromagnetic field. But still, there are some problems. Okay, so now that we have set the 2 points of view, let's go to try to put them together. And putting them together is this Bohr's correspondence principle. So this means that we want to show on one end that if we take the limit h bar to 0 of the quantum theory, we recover the classical theory. So starting from the Pauli first Hamiltonian, taking h bar to 0, we recover the Newton-Maxwell equations. So this is on one end. And on the other end, we want to use the Bohr's correspondence principle and the quantum dynamics to define classical trajectories. So we want to take to see how it's possible to define classical trajectories that are driven by the quantum flow. So they are identified by the quantum flow. And I think that this is quite interesting if you think about it, rather natural. So in some sense, it's like we need a regularization. So think only of the electrostatic problem. The Coulomb potential is too singular to be treated classically. So it can be, but it can be treated quantum mechanically. So to define the motion in the Coulomb potential, we go through the quantum. And so we lift the problem to a quantum problem, we follow the quantum dynamics, and then we go down to the classical level by means of the Bohr's correspondence. This is the idea, and I will try to make it even clearer very soon. So in particular now, let me start by formulating this classical result that is driven by the quantum. Okay, so this is a first theorem that we prove in this paper that was, the reference was in the first page with Ziad Ammari and from Hiroshima. That is recent, is of this year, early this year. Okay, so as you see, and as I previewed before, we are able to relax. So for the moment, we are only able, okay, so the result by itself classically is not astonishing. Is not overwhelming because we just relax a little bit in the classical problem the regularity assumption, or change a little bit the regularity assumption on the charges. It's not exactly relaxing because there is this infrared part that you did not see before. Okay, but it's still an improvement because, as I said, if you take this, charges with this regularity at the classical level, we don't know, apart from our result, how to prove this in another way. So we try to think about using a standard PD, ODE techniques that are used to prove that global well-posedness, and they don't work. You cannot really even make the basic fixed point argument to get a local solution. So maybe there are some more refined techniques that could work that we are not aware of. But let's say standard techniques that used to work with other regularity assumptions on rho don't work anymore. And to me, this is an indication that indeed taking this quantum detour, as I call it, so going through the quantum dynamics to define the classical dynamics, it's a good idea. In the sense it could be useful, especially to deal with the more interesting problems of small charges or even point charges, if one could understand point charges also at the quantum level. But this will be in the outlook at the end of my talk. So let me postpone to that. Okay, but anyway, so this is the result that we have. So we change or relax, if you want, a little bit the regularity for the charge distributions compared to the standard classical well-posedness, but still we are able to prove well-posedness. So we are able to prove well-posedness for E and B in this H sigma, with sigma between 0 and 1/2. So we can go from L2 to H1/2 by taking these charge distributions that are with this regularity. So if we have H.1, so sigma equal to 0, we are actually in the same result as the, well, it's a bit better here because it's well-posedness in L2 instead of H1/2. No, sorry, it's, yeah, sigma equal to 0. We have L2 here instead of H1/2, but here we have H.1 intersection with H.-1, so this is a subset of H1 actually. That was the condition at the classical level. So the classical level, we had H1 implies well-posedness in H1/2, H1/2. Here with sigma equal to 0, we have a subset of H1 implies well-posedness with E and B in L2. So a bit less regularity for E and B. But for sigma equal to 1/2, that becomes more interesting because here for the ultraviolet part of rho, we have H.1/2 only, not 1. Still, we are able to prove well-posedness in for E in H1/2 and B in H1. So we are relaxing at least the ultraviolet regularity required to discharge. But as I said, more than the result itself, it's the strategy of proof that I find very interesting for this theorem. And the strategy of proof that then I will be a bit more precise towards the end of my talk, if I have time, is this one. Okay. So the idea is that we take a quantum detour. So we start from an initial condition at the classical level. So initial position, momenta, and values of the electromagnetic field. We lift this to a quantum state, gamma h bar, that is as classical as possible and as classically as possible concentrated around this classical solution. So we will take what is called a coherent state of minimal uncertainty, morally. I will be more precise later. At the quantum level. So at the quantum level, we have a state that is as close as possible to the classical state, to this classical condition, and we let it evolve by the quantum dynamics. The Pauli-Fierz Hamiltonian drives this state at time t. We take then the limit h bar to 0 of this state at time t and recover a classical point in the classical phase space at time t. Well, and this point at time t will define this Newton-Maxwell flow. So we will show that actually this UT satisfies in some sense the Newton-Maxwell equations, or in a pretty strong sense actually, and so it's a solution of the Newton-Maxwell equations that we have built going through the quantum. I will try to tell you more details afterwards, but before doing that, let me go to the main ingredient of this theorem, that is this arrow here actually, or if you want this part. So being able to take the classical limit of this Pauli-Fierce Hamiltonian or Pauli-Fierce dynamics. And this is what we call the Bohr's correspondence principle. Okay, so let me start with a quick overview. I don't know how much time I have, Max. I started a bit later, unfortunately, but if I have to cut short, let me know.
You have 30 minutes or so, and then I'll have to leave. So just take your time. I don't know how many, 15. So I think you should be able to finish, no?
Yeah, I should be able to. If it's 15 minutes, I'm able to finish even before, probably. Okay, so let me go. Okay, so what is the idea of semi-classical analysis for quantum fields? It's mutuated from the one for particles that is maybe better known to you. And here we have to combine the two. Anyways, we have a quantum state that is, as I said, a positive trace class operator on the whole Fock space of the system. L2 is the particle part. This gamma S is the Fock space, symmetric Fock space, and it's the fields part. So on one end, we have a quantum state that is this type of object, and on the other end, we have a classical state that is a probability measure on the phase space. And the phase space corresponding to this system is the space where we have variables, the position of all the particles, the momentum of all the particles, and then these alpha 1 and alpha 2 that are the classical counterpart of the creation and annihilation operator. So if in this object you substitute A and A star with alpha and alpha bar, and you forget about the heads, so you consider everything as ordinary classical objects, you obtain the classical electromagnetic potential. Okay. So these are the natural variables in semi-classical analysis for the electromagnetic field. You can reconstruct E and B by constructing the electromagnetic vector potential by this alpha 1 and alpha 2. Then taking the time derivative, you will get E, and taking the curl, you will get P. So the original variables that we consider can be reconstructed by this. So actually, having a measure here, you also have a probability measure on the space for phase space for QP, E, and B as variables. Okay. Then the idea is that if you go from quantum to classical, so if you take the limit h bar to 0, your quantum state gamma h becomes some probability measure on the space of classical configurations. And this, we say, if this is true, so if this gamma as a state converges to the probability measure, I will tell you how the convergence is realized very soon. We say that mu is a Wigner measure. This is a terminology mutuated from standard semi-classical analysis of this state gamma h. Okay. So how you can say that a quantum state converges to a classical state is by means of the Fourier transforms. So we can define a non-commutative Fourier transform for this state gamma h by taking the trace of this gamma h with the Weil operator, that is the complex exponential of the so-called field operator. So is this exponential e to the I, pi is the pi, the number pi, and then you have that we need for well, normalization motives to get the correct answer in the end. you take the product of P, that is the classical P that is in this U alpha here, and then the quantum position operator Q. Then you take the product of the classical position Q with the momentum operator P for each particle, and then you do this A1 of alpha 1 means the integral of A1 of K alpha 1 of K, where A1 is the annihilation operator. Then you do the same for the second polarization, and then you do the same for A star. Here there is a star that I forgot. I'm sorry. This is a star. Okay, so A star 1 and A star 2 as well. This is called the exponential of EI. This guy is called the Weil operator for the field, and this is the Weil operator or translation operator, phase space translation operator for the particle. So this is called the non-commutative Fourier transform of gamma. It depends, is a function of this configuration U alpha, where U alpha is this Q, this P, and this alpha 1, alpha 2 that are here. So it's a classical point in the classical phase space. Okay, so this is a function, a complex valued function of the classical phase space, but built up from the quantum state. On the other hand, classically, we can take of a probability measure the Fourier transform. This is also a complex valued function of the classical phase space that we obtain by integrating e to the 2 pi I, the real part of the scalar product of this U alpha with Z, integrated over all possible Z weighted with the probability measure mu. Okay, so by taking these Fourier transforms, we are making the quantum states and classical probability measure on the same grounds. They are both functions of the phase space with complex values. And so the convergence means that the pointwise limit for every point of this non-commutative Fourier transform equals the classical Fourier transform of a measure. And if we know the Fourier transform, we have the Bochner's theorem that allows us to say exactly what is the measure mu. Okay, so in this way we can identify the Wigner measure mu associated to gamma by taking this limit. Okay, and on the other hand, let me be pretty quick here, so I want to arrive to the end. We have the classical symbols, so we have classical functions of the phase space that we can lift to operators by taking the quantization. So for the particle part, we can take any quantization you want that you are probably familiar with. On the field, we are a bit constrained because these fields are have infinitely many degrees of freedom. So the semi-classical analysis there is more difficult to do. We don't have tools like Fourier transforms, Lebesgue measures, and so on. So what we can do is just this so-called Wick quantization. Wick quantizations means that you replace every alpha with an annihilation operator, every alpha bar that appears in your symbol with the creation operator, and you put all the creation operators on the left and the annihilation operators on the right. It's also called the normal order. Okay. And if you do that, what you can do is that for shootable symbols, you can prove that if your state converges to the Wigner measure mu, the expectation on your quantum state of the quantum operator FH, that is the quantization of the symbol F, converges to the integral with respect to this probability measure mu, that is the Wigner measure of the classical function. Okay, and by exploiting this convergence here, we are able to prove the so-called correspondence principle. So the correspondence principle tells us that we have this type of commutative diagram. Okay, so if we start from gamma h, so from a quantum state, and we take the limit, we obtain the corresponding Wigner measure mu0. Then if we make mu0 evolve with this Liouville equation. I will be more explicit soon, but okay, so there is an evolution that is a Liouville type evolution, a transport equation for this measure. We can go to the measure mu t. Okay. On the other hand, we obtain the same result if we first evolve gamma with the Pauli-Firth dynamics and obtain gamma t, and then take the limit. Then to gamma t, the associated Wigner measure is this mu t, that is the evolution, the push forward of this measure mu zero by means of this Liouville flow. Okay. And here you can find the reference that for coherent states, you have a result similar to this, but much less general, that was given by Antti Knowles in his PhD thesis in 2009. Okay, so some remarks quickly. So this evolution mu t is dictated by the Liouville transport equation associated to the Newton-Maxwell system, the classical Newton-Maxwell system that we defined at the beginning of the talk. Okay. And this Newton-Maxwell flow solves, but in a very weak sense, the Newton-Maxwell equation, in a much weaker sense than the one that is stated in Theorem 1, even if I did not state it exactly. But in Theorem 1, we have global well-posedness, so essentially solution of the integral equation. While here we have a very weak solution, a solution of the transport of probability measures. So you have to test with very smooth and nice test functions. Is a very weak solution in some sense. Okay. So thanks to the correspondence principle, we have a notion of weak solution. So we have that starting from a semi-classical Wigner measure, so a measure obtained by a quantum state, we can evolve it with this weak Liouville flow, dictated in some sense by the Newton-Maxwell equations, and obtain a solution at time t. Okay, and this theorem is a so-called Igorov type theorem, so it's less powerful than the Igorov theorems that you have in standard semi-classical analysis, but is in the same spirit for these fields, so these infinitely many degrees of freedom. Okay, so let me come back now to this Theorem 1 that I said, so this quantum-driven classical trajectories, to give you some ideas of how to prove this, and this will conclude my talk. First of all, we need a result of a priori uniqueness. So we need to know a priori that if the charge distribution has the regularity that we wanted in Theorem 1, there is at most one solution of the Newton-Maxwell equations. And this is a result that we can establish by purely classical means a priori. Then we use the Liouville flow. So the Liouville flow that we obtained by the Bohr's correspondence principle. So the fact that there exists one solution of the Liouville equation is given by this Theorem 2, by this Bohr's correspondence principle. Combining that existence of this solution of the Liouville equation with the a priori uniqueness, we have that there exists and is unique a solution in the stronger sense, in the sense of the integral equation of the Newton-Maxwell equation. And this is true for mu0, almost all conditions, initial conditions u0. So apart from sets of measure 0 in the Wigner measure mu0, we have existence and uniqueness of a solution. And this implication, this result of implication here is given in this very nice paper by Clément Roufort, that is a former PhD student of Ziad Ammari, in this reference that is here. Okay, so now we have that thanks to this Liouville flow given by the Bohr's correspondence principle, so by the quantum detour, combining with this a priori uniqueness, we have existence of solutions of the classical Newton-Maxwell equations with this new weaker regularity, but only for mu0 almost all initial data. So not for all, we don't have yet global well-posedness. We don't have at this stage uniqueness for and existence of solution for every initial condition. But then we can saturate the initial conditions using coherent states. these coherent states of minimal uncertainty that I already told you about. I don't want to define them because it will take too much time, but you can define these coherent states. It's very standard. So for any given classical configuration U0, there exists this coherent state of minimal uncertainty, gamma h of U0, such that the Wigner measure associated to it is the Dirac delta, so the measure concentrated exactly in the point U0 of the classical phase space. So we can saturate with delta measures the whole phase space, and following this delta measure by the Liouville equation, we will have a flow that arrives to another measure concentrated in a single point that will be our UT. And since we can do these measures are, of course, clearly of measure 1 in U0, we can really saturate all possible initial conditions and indeed prove the global well-posedness that we wanted. So this concludes the proof of Theorem 1. And let me conclude quickly, I think I am on time, with a quick outlook. So we could apply these same ideas to other models that are maybe less interesting physically, like this Fröhlich polaron, but where these ideas of needing to go through the quantum to obtain the classical features is really even more necessary. In this Fröhlich polaron, there is no ultraviolet cutoff, so we cannot play with regularity of these distributions of charge. There, the distribution of charge is really point-like, and it's, to my knowledge, impossible to prove that the classical system is well-posed, but we have hoped to go through this quantum dynamics that is indeed well-posed on the other end. So there is the idea, and we plan to try to apply this to other models where this, the importance of going through the quantum to regularize the classical flow is even more transparent. Then there is the point of the diamagnetic inequality. So classically, the diamagnetic inequality is inequality. So the ground state energy, if you take the vector potential to be 0, is equal to the energy, ground state energy, if you take the vector potential non-zero. While at the quantum level, if you take the vector potential to be 0, you have a strictly smaller energy at the quantum level, ground state energy, than if you take the vector potential to be non-zero. So one should understand why in the limit, this strict inequality actually flattens to an equality, why this happens. Because this inequality is very much important at the quantum level to prove stability properties of the system that are indeed lost at the classical level. So this means that one could understand how these stability properties are lost in the classical level. Then what we would like to do is to understand or put on solid mathematical ground this paper by Monister and Sharp on very small charges where there are these runaway solutions. So can we see these runaway solutions or these non-causal solutions emerge concretely when we take the classical limit if we have a small radius? This is something we would like to understand. And finally, the most ambitious task, of course, will be to understand what happens to point charges, both at the quantum and the classical level. Okay, so let me conclude here by thanking you for your attention and apologizing again for having been late to the meeting. Thank you.
Oh, thank you very much, Marco. Does anyone have any questions?